Doris. She loves Satie, remember? We brought her some Satie music. Hello? Sorry.
Dynamical systems as we teach them is a very strange subject. We give you this beautiful story about how errors grow with time, and when systems are unstable, after some time we lose all the information. But if they're confined, they have to keep coming back, and we can count half and they come back. Logarithm of that is called entropy. And that's the usual story of chaos that we give in TED Talks, on television, and in undergraduate and graduate dynamical systems classes. It's a weird talk because mentally we haven't really gone very much beyond Newton when we do this. As a matter of fact, almost nothing that's been done in 20th century, like quantum mechanics, quantum field theory, statistical mechanics, is included in this story. So our story is always Hamiltonian. What this means is that we take a phase space, which is characterized by some coordinate q and the dual momentum p. We start someplace in this phase space. Boom. And then we let Hamilton's equation do the wonder. And what they do is they trace out a trajectory, and at some time t, we are here. So if you started at x in a phase space is a pair of these positions, and momenta could be 3 dimensions, could be 6, usually some small number in celestial mechanics at least. We find ourselves time t later someplace else. And that's how we tell our story. Now, if you're a little bit more sophisticated, we tell you that actually we need to find very special kind of orbits. The ancients always insisted on them, and Poincaré insists on them, so that as we continue, after some time, the orbit comes back, meaning that this is same as x time t later. Let's call it capital T for the period. Let's call this periodic orbit P for periodic or prime, time of return TP. And then one thing that we learn when we need to compute them is that we actually have to look not only just at the orbit itself, but its neighborhood as well. So we look at a little neighborhood. We let it run around, sometime t, the neighborhood, someplace here, then it's someplace here. And finally, when we come back, it's where it used to be, but its shape has changed, because it turns out that some neighboring trajectories are approaching our trajectory and other ones are going away. That means the system is hyperbolic. It's unstable in some directions and stable in other directions. And we characterize this stability by a matrix. So this is a linearized flow centered on the periodic orbit, which in some sense is exponential, an operator that moves the neighborhood around, some kind of derivatives, and it comes back at time t. And then we discovered that the important thing, especially when we are trying to find periodic orbits, so whenever you're trying to find orbits which at time 0 are the same as at time t later. Then this linearized neighborhood, take derivatives of it. These are all vectorial quantities because phase space has some number of dimensions for state space. And the derivative of this thing that comes back is called the Jacobian, or the prime orbit. And the periodicity condition means that, acting on the neighboring trajectories, P's and Q's, we have to have 0. And then if you're doing a Newton calculation, for example, we make a guess and we come close, we want to improve that guess. The Newton calculation requires computing the first derivative, is this quantity here, and then inverting it to get a better calculation. And that leads us to consideration. Whenever you invert a matrix, you have to compute its determinant. The considerations of determinant of identity minus the neighborhood squeezing and stretching for one period. And that's a kind of thing that then one interprets quantity 1 over determinant over 1 over minus j, this quantity here, can be interpreted as the size of the neighborhood that comes back after one iteration. So this turns out to play a very important role in Hamiltonian dynamics, evolution forward in time. And this is the size of the neighborhood, p-orbit neighborhood. And this is a very important object because this essentially tells you, which fraction of initial trajectories after one period still can be identified as belonging to this periodic orbit. And this neighborhood can be very wide in some directions. These are stable directions, meaning all the points in these directions fall into the orbit. And very thin in other directions, which are called unstable directions. And the beautiful thing about the determinant, it doesn't depend on the coordinates in which we compute our system. So this determinant is actually an invariant characterization, true in any representation of same dynamical systems, Cartesian, polar, any nonlinear coordinate. This thing is always the same. So it plays an important role in everything. And our story about chaos kind of ends here. Imagine how amazing this is. Now, if you're an honest person, you actually also have to compute this for particular systems. And it turns out that if you don't just talk like a professor, but work like a graduate student, you very quickly learn that you have to do something totally different. So the actions are very different from. If you actually do these calculations for almost any non-trivial system, you'll discover that this matrix you're looking at has entries in it which are growing exponentially with time, exponentially, decreasing exponentially with time. And in a very simple example that we published in probably Physical Review Letters, we know that size of these entries in that matrix is 10 to the 130 orders different. That means to compute this matrix, I can write it, you have to have 140 digits of precision. Now, you can say this, but once you start applying this to turbulence, field theories, fluids, where you already have many degrees of freedom for the system, it's totally illusory to think this way. So it turns out that all along, we've been doing something totally different.